Nature, in its relentless pursuit of efficiency, does not typically indulge in biological extravagance without a purpose. Yet, when we are confronted with the skull of Parasaurolophus walkeri, we face a structure that seems to defy this principle. Here is an animal that invested enormous metabolic resources into growing a long, hollow, bony tube that extended nearly a meter from the back of its head. This crest was not a simple horn or a solid display piece. It was a complex, internally partitioned apparatus. It presents an immediate and profound scientific paradox. Why would a large herbivore living in an ecosystem patrolled by apex predators evolve such a cumbersome and seemingly impractical feature? This isn't just a dinosaur. It's a paleontological puzzle box, a cold case 75 million years in the making. Now, let's dissect the evidence and solve the case of this bizarre survivor. Parasaurolophus was a genus of hadrosaurid, or duck-billed dinosaur, that inhabited North America during the late Cretaceous period. It was a large, primarily bipedal herbivore, a creature whose survival depended on its ability to find food and avoid becoming it. The fossil record provides a clear picture of its general anatomy, which, apart from its head, was typical for a large ornithopod. But the skull commands our full attention. Let's examine a 3D digital model of the holotype skull. The crest sweeps back from the snout in a graceful curve. It is a paired structure, formed from elongated premaxillary and nasal bones, fused together. Early paleontologists were equally perplexed. The initial hypotheses, while creative, have been systematically dismantled by modern analysis. One of the first proposals was that the crest functioned as a snorkel, allowing the animal to breathe while submerged in water. However, if we look at a cross-section of the crest, we can immediately identify the flaw in this theory. The distal end is completely sealed. There is no opening for air intake. Another idea posited the crest as an offensive or defensive weapon. A simple biomechanical stress simulation, which we can visualize here as a color-coded pressure map, demonstrates that the hollow, thin-walled bones would have been too fragile for combat, likely fracturing on impact. So it wasn't a snorkel, nor was it a club. Could it have been an external air reserve? When we calculate the internal volume of the crest, we find it was insufficient to provide a meaningful respiratory advantage for an animal that weighed several tons. The paradox deepens. We have a structure that is metabolically expensive to grow, makes the animal more conspicuous, and offers no obvious advantage in combat, respiration, or foraging. The solution to this case file does not lie in these superficial explanations. The answer, as is so often the case in biology, is hidden within the structure itself. The intricate internal architecture of the crest is the most compelling piece of evidence we have. Having eliminated the most obvious external functions, our investigation now turns inward. The key to this case file lies concealed within the bone itself, and for decades, this internal architecture remained largely a matter of speculation. However, with the advent of high-resolution computed tomography, or CT scanning, we can now digitally dissect these fossils layer by layer, revealing their secrets without ever touching a drill to the specimen. When we apply this technology to the crest of Parasaurolophus, the paradox of its existence begins to resolve into a masterpiece of biological engineering. Let's load the CT scan data into a 3D modeling environment. On the screen, we can now peel away the outer bone, revealing the intricate network of tubes within. What we see is not a single, simple chamber. Instead, we find a pair of primary dorsal tubes that travel from the nasal openings all the way to the distal tip of the crest. Here, at the apex, the passages form a U-bend and loop back down through a series of more complex, smaller, and interconnected chambers before finally connecting to the airway leading to the lungs. We can trace this complex route with an animated overlay, showing the path a single breath would have taken, in through the nostrils, up the crest, around the bend, and back down into the skull. This specific configuration is biomechanically significant. A long looped tube is, in principle, a resonator. Its geometry is strikingly analogous to the construction of brass instruments, like a trombone or a French horn. Let's break this down with a 2D diagram. If we were to hypothetically unroll the passages of the crest, we would have a tube of a very specific length. In physics, the length of a resonating tube is the primary determinant of its fundamental frequency. Longer tubes produce sound waves with longer wavelengths, which we perceive as lower pitches. The crest of Parasaurolophus walkeri, for instance, contained tubes well over 2 meters in length. This anatomical blueprint is not for breathing efficiency. It is a blueprint for sound. To test this hypothesis, we can move beyond simple analogy and into the realm of computational simulation. Using a highly detailed wireframe model of the internal crest anatomy, we can apply the principles of computational fluid dynamics to simulate air being pushed through the structure from a larynx-like source. This animation visualizes the resulting pressure waves. The simulation confirms that as air passes through the serpentine passages, a standing wave is generated. The crest acts as a powerful low-frequency resonator, amplifying and giving a unique tonal quality to any sound produced at its base. The models predict that Parasaurolophus was capable of producing powerful, sonorous calls in the range of 30 Hz, a deep resonant sound at the very bottom edge of human hearing, bordering on infrasound. Sounds in this low-frequency range have a distinct physical advantage. They travel for immense distances and are less impeded by physical obstacles like dense foliage, making them ideal for long-range communication. The evidence becomes even more compelling when we conduct a comparative analysis. Paleontologists have identified at least 3 distinct species: Parasaurolophus walkeri, P. tubecan, and the short-crested P. curticrostatus. Let's place 3D models of their skulls side by side. The external differences are obvious, but the crucial variations are internal. A comparative diagram of their internal tube lengths reveals a clear pattern. The long, elaborate crest of P. tubecan would have produced the lowest frequency calls. The intermediate crest of P. walkeri would have produced a slightly higher pitched call, and the much shorter crest of P. curticrostatus would have generated the highest frequency of the 3. This morphological diversity, directly correlated to a predictable difference in acoustic output, is the paleontological equivalent of finding a collection of musical instruments in different sizes: a tuba, a trombone, and a trumpet. It strongly suggests that the primary function of the crest was not only to create sound, but to create species-specific sounds. Furthermore, some specimens show slight variations in crest shape that may correlate with sex, a phenomenon known as sexual dimorphism. If this is the case, the crests may have also produced individually distinct or sex-specific calls within the same species. Our biomechanical investigation, therefore, delivers a clear verdict on the how. The crest was not a snorkel or a weapon. It was a sophisticated, finely tuned acoustic device. The evidence for this is written in the very structure of the bone, confirmed by the laws of physics, and reinforced by the diversity observed across the genus. The question that remains is the most fundamental one. Why? What was the evolutionary purpose of this prehistoric trombone? Our biomechanical investigation has provided a powerful verdict on how the crest of Parasaurolophus functioned. It was a finely tuned acoustic resonator. We have deconstructed the instrument. Now, we must synthesize this physical evidence with the principles of evolutionary biology and paleoecology to address the ultimate question: why? What selective pressures drove a creature to evolve a biological trombone on its head? The answer likely lies in the complex social dynamics of these herding animals. The most direct and well-supported hypothesis is that the crest was a tool for species recognition. As our comparative analysis in the previous section demonstrated, the distinct crest shapes among P. walkeri, P. tubicen, and P. certocristatus would have produced species-specific call frequencies. In the complex ecosystems of late Cretaceous North America, multiple species of large herbivores, including other types of hadrosaurs, often shared the same territory. Let's visualize this with a simple ecological diagram. In a dense forest, or during twilight hours, where visual identification is difficult, an unambiguous acoustic signal would be the most effective way to locate and attract a mate of the correct species. The crest, in this context, was an evolutionary safeguard against hybridization and a guarantee of reproductive success. Building upon this, a second major hypothesis centers on intraspecies communication and herd cohesion. Fossil trackways suggest that hadrosaurs were social animals that moved in large groups. Coordinating the movement of a herd, especially one spread out over a large area or through dense vegetation, requires effective long-distance communication. The low-frequency sounds produced by the crest were perfectly suited for this role. As we can illustrate with a wave propagation schematic, these long sound waves would travel for kilometers, penetrating foliage that would scatter higher-pitched sounds. A single call could signal a change in direction, the location of a food source, or, most critically, an alarm. A deep, resonant blast from a watchful Parasaurolophus could have been the difference between life and death for the entire herd when a predator like Gorgosaurus was near. Finally, we must consider the powerful evolutionary force of sexual selection. In many living species, extravagant structures, from the antlers of a stag to the tail of a peacock, function as honest signals of an individual's fitness. The crest of Parasaurolophus was likely no different. It served not only as an acoustic instrument, but also as a prominent visual display. A larger, more robust crest may have signified a healthier, more dominant individual to potential mates. The acoustic properties would be part of this display. A male capable of producing a deeper, more powerful, and sustained call might have been perceived as a superior mate. These three hypotheses, species recognition, herd communication, and sexual selection, are not mutually exclusive. In fact, the most logical verdict is that they represent a suite of interconnected functions. The crest did not evolve for a single reason, but as a comprehensive social signaling package. It was an acoustic and visual identifier that allowed these animals to find each other, stick together, warn each other of danger, and select the best possible mates. The bizarre structure was the very foundation of their complex social lives. While the precise nature and nuance of their calls are lost to time, the evidence embedded in the bone allows us to understand the purpose of the music, even if we can never hear it. The case of the Parasaurolophus crest reveals a profound truth about evolution. What first appears as a bizarre, inefficient appendage is, upon investigation, a sophisticated solution to the complex problems of communication and social living. It is a testament to nature's ability to innovate, turning the simple act of breathing into a symphony of survival. and it reminds us that some of history's greatest stories are still waiting to be heard, encoded in the silent language of bone. What is your hypothesis? Do you think the crest was primarily for species recognition or for social display? Leave your analysis in the comments below. And if you want to own a piece of this investigation, the detailed 3D model of the P. walkeri crest we analyzed is available for our patrons via the link in the description.